Today's lesson is on right triangle trigonometry. The essential question for this lesson is, how do you evaluate trigonometric functions of acute angles, and how do you use the fundamental trigonometric identities? Now, since we are talking about right triangle trigonometry, we need to initially start off with a right triangle. And as you can see in the picture here, we're talking about angle theta, and we have a right triangle, and we have labeled the sides. The hypotenuse, HYP, the side opposite the angle, and then the side adjacent to the angle, okay? Now, obviously, if we had picked the other angle, the opposite and adjacent would be switched, but for our purposes, let's consider this to be the triangle where the angle shown is theta. Now, you may remember from prior classes that you can use the right triangle and the name SOHCAHTOA to take and give you what how do you determine the sine, cosine, and tangent using a right triangle. And obviously this shows that the sine, SOH, is equal to the opposite over hypotenuse. The cosine, CAH, is equal to the adjacent over the hypotenuse. And the tangent, TOA, is equal to the opposite over the adjacent. Now, but this only covers the basic three trig functions, sine, cosine, and tangent. There are also secant, cotangent, and cosecant. What are they equal to in terms of a right triangle? So the first of these is cosecant, and cosecant is defined as being equal to the length of the hypotenuse over the length of the side opposite. Now, if you look at this, you'll notice this is the exact inverse of sine. Sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. The next function is secant theta, and secant theta is defined as being the hypotenuse over the adjacent. Again, notice that this is the exact inverse of what cosine is. Cosine is adjacent over hypotenuse. Secant is hypotenuse over adjacent. And then the last of the six trig functions is cotangent, and that is equal to adjacent over opposite. And as you might expect, this is the exact inverse of what tangent is. Tangent is opposite over adjacent. Cotangent is adjacent over opposite. So now let's talk about some special triangles which will enable us to come up with trig functions of a few special angles. The first of these triangles is the 45, 45, 90 right triangle, as you can see in the image. Now, obviously, since it's a 45, 45, 90, it's an isosceles right triangle. So if we assume that the legs are equal to 1 in length, then the hypotenuse in this case is equal to the square root of 2. And you can verify this by using the Pythagorean theorem. So let's say that using the definitions on the previous page, we would like to find what the sine of 45 degrees is. Okay, so we have a triangle here, 45, 45, 90 right triangle, and we want to find out what the sine of 45 degrees is. Well, again, as I say, if we use the definitions on the previous page, sine is equal to opposite over hypotenuse. So the side opposite the 45 degrees is obviously equal to 1. And the hypotenuse is equal to the square root of 2, so therefore the sine of 45 degrees is 1 over the square root of 2. Well, as you might understand, that's non-standard. We don't want radicals in the denominator. So if we multiply by the square root of 2 over the square root of 2, we end up with our final simplified version. Sine 45 degrees is equal to the square root of 2 over 2. Now we could use the other definitions to also find cosine 45, tangent 45, cosecant 45, secant 45, and cotangent 45. So the second of our special triangles is the 30, 60, 90 right triangle. And as you can see in the image, the shortest side is going to be the side opposite the 30 degrees. So if the side opposite the 30 degrees is equal to 1, the hypotenuse is twice that, or 2, and the other leg is simply going to be 1 times the square root of 3. So our sides for a 30, 60, 90 triangle are 1, 2, the square root of 3. Now again, if we want to find the trig functions, say we want to find the cosine of 30 degrees. So again, as you recall, the cosine is equal to the adjacent over the hypotenuse. So for cosine 30, the adjacent leg is square root of 3, the hypotenuse is 2, so the cosine of 30 degrees is equal to the square root of 3 over 2. Now similarly, if we were asked for the cosine of 60 degrees, again, remember that it is adjacent over hypotenuse. So for 60 degrees, the adjacent side is 1, the hypotenuse is again 2, so the cosine of 60 would be 1 over 2. So using these two triangles, these two special triangles, we can get all 6 trig functions for 30 degrees, 45 degrees, and 60 degrees. Now, in trigonometry, we've defined all the 6 trig functions. Now, we understand that there are some basic relationships between these trig functions, and these are identified in the fundamental trigonometric identities. Now, some of these I've already alluded to, but now let's just write them down as identities we need to remember so that we can use them in applications. Now, as you recall, when we were talking about sine and cosecant, remember that how I said one was the inverse of the other. Well, this leads us to the first identity, and that is sine theta is equal to 1 over cosecant theta. Now, similarly, cosine theta is equal to 1 over secant theta. And finally, we've got tangent theta is equal to 1 over cotangent theta. Now, these are referred to as the reciprocal identities. Now, obviously, we take each of these and solve it for the cosecant, secant, and cotangent, and have the similar reciprocal identities for those. But if you remember these and know how to take and convert it for the other trig function, you should be fine. The reciprocal identities. Now we have the first of our quotient identities, and this is that tangent theta is equal to sine theta over cosine theta. Now if we've got tangent, we also have cotangent. So cotangent theta is simply equal to cosine theta over sine theta. These are the quotient identities. Now the first of the Pythagorean identities says sine squared theta plus cosine squared theta equals 1. It's almost like the Pythagorean theorem, a squared plus b squared equals c squared. So in this case, sine squared theta plus cosine squared theta is equal to 1. Now the second of these identities is 1 plus tangent squared theta is equal to secant squared theta. And finally, the last of the Pythagorean identities, 1 plus cotangent squared theta is equal to cosecant squared theta. Now let's look at an example to see how we can apply some of these trig identities. So let's say we're given that the sine of theta is equal to 0.6, and we want to find the value of cosine theta and tangent theta. So looking back at the identities, which identity has just sine and cosine in it? Well, if we look, we can see that sine squared plus cosine squared equals 1 has sine and cosine in it. So if I plug in the value for sine theta, I can find cosine theta. So once you plugged in 0.6 for sine theta in sine squared plus cosine squared equals 1, you'd have 0.6 squared plus cosine squared equals 1. If you do the math, you would get a result that cosine theta would equal 0.8. Now, if you were asked to find tangent theta, you now know sine theta, you know cosine theta, so you could use the formula that we had earlier of tangent theta equals sine over cosine and figure out what tangent theta is. So that would give you all 3 of the basic trig functions from knowing just one. There's one other type of example which you might run into, and where you use trig identities, and that is where you're given a statement and you're asked to manipulate it so that you get one side of the equal sign equal to the other side. Let me just give you an example here. Let's say I gave you the following equation, and that is sine theta times cosecant theta is equal to 1. And I want you to prove that that is a true statement. So basically what you have to do is manipulate the trig functions on the left so that they look like the trig functions on the right. Well, we do have some identities here that we could deal with, and for example, cosecant theta is simply equal to 1 over sine theta, so let's substitute that in. So now if we look at this, we can immediately see that our sine thetas would cancel out, and we would end up with 1 equals 1, so therefore basically we would have proven this equation as being true. Now here's a problem for you. Given a triangle, as you can see, we know that the angle A is equal to 18.4 degrees, that side A, which is lowercase a, is equal to 4 feet. That's the side opposite angle A. I want you to find side B and side C, and you should be able to do this using what you know about trigonometry. And once you get those two answers, post those answers in the drop box. Thank you.